Oh, whoopsies. There we go. That should pull up. Ooh, cool. Okay. Well. Welcome in. So today, we have a continuation of our Sunday morning paper that we started last week. We're just gonna do a quick recap of what we did. And try and get a little bit further. I do have to get a bunch of work done, so I'm not gonna go like super long on this stream, but yeah, let's see if we can make our way a little bit further into our paper here. This is a fairly intense paper. Let's see if I scroll in a little. Does that? Yeah. We can see things now. What? Crazy. I should hook up my thing, shouldn't I? Okay. Give me 1 second. I'm going to hook up my. I realize for this paper, I really need my my tablet with the little pen on it. It's actually like an art tablet thing, but I use it for math. So give me half a second. I'm just going to move. So things might get a little wonky for a moment. I'm just going to move this over here. How does that look on, let's see. Oh, okay. So we're still seeing it pretty clearly. What we can do is just extend it just a tad, make it a little bit bigger. Like this. Actually, we can just do like that, and then I could potentially even scroll out, and it would still be visible. Hold on, complete transition. Let me give me a second to do this. Okay, and then I can scroll out a little bit, and so you should be able to still see things even when I have writing area to take notes. Okay. So, what are we actually doing here? Well, for us, for our purposes, we're just trying to learn how to do path integrals in Wigner spaces, right? Wigner distributions. This parallels something that I'm getting into later over time, but suffice to say, for now, we're just trying to understand this, right? We're just trying to get a basic concept of how path integrals function, especially in something like a Wigner space. Because again, that has applications for other things later. Right. So, we went down to, okay, Wigner or Boltzmann or Fermi statistics. Okay. Here's our math. Here's what we were looking at. So let's just re-look at this math really quickly to re-understand what's going on, to give us a little bit of a give us a little bit of background as we're moving forwards, right? So we are looking at a quantum operator A, and so an operator can be something like the Hamiltonian, right? It can be something that's over here. It can be something like position. Position is an operator in quantum mechanics. It is the representation of things that are observables, right? So any measurement of something is defined as an operator. So it can be a whole bunch of different things, right? So this is a arbitrary quantum operator, A hat. That operators typically have a hat on top, a little carrot hat on top. So it can be written as Vile's symbol A. So now we're going from an operator into this function, right? A of P, where P is momentum and Q is location. I don't know why Q is location. That's just the it's just a pretty standard designation. Again, why? No clue. But anyway, okay. So if we want to know what the right, and it's going to be average. So again, we're trying to find the average value over a phase space with Wigner function this, right? So again, a phase space is some representation of a set of variables. So you can plot velocity versus position, for example. You could plot mass versus or apparent mass versus velocity. You any of a number of different things, right? It's just a space where you represent some variables in a kind of geometric way that allows you to look at it. Chase is 007. Yeah, I don't know why Q is like the stereotypical thing in quantum mechanics for some or rather not in quantum mechanics, in statistical mechanics. Q is just used for position. No clue why. It just is. Okay. So what are we looking at for this? There's a couple of hints that we can look at. This so obviously we are going to be taking an integral, and that integral is going to be over all momentum and all position space. Okay, so we are summing up the 2 pi h bar to the 3n. This is just a constant, right? This is a normalization constant. But we are integrating over all space. So what that means is we are finding our average over all position and momentum space. Now, if you notice, it's 3n and 3n. Why is it 3n? Well, n is the number of particles that you're looking at, and then there are xyz for position and xyz for momentum and xyz for position. So there are 3n different degrees of freedom, so dimensions within this phase space. Okay, so we're integrating over all of it, all the possible positions and momentums that these particles can have. And all we're saying is that our average is just this, whatever this function is, right, that we've converted our operator into. We're saying that the average output of the operator is this function version of the operator times the distribution, W, right, the Wigner function, and then we integrate over all of it, right? So the Wigner function is essentially telling you, it's kind of giving you a distribution, a way to look at how A is varying, not just in P and Q, but also in beta and V, right? And so that is going to get us our median, or our mean, sorry, our average of this operator, which again could be position, could be momentum, could be the Hamiltonian, could be whatever, right? So kinetic energy, or energy, I'm sorry, total energy, could be any of these things. Okay. And so now we have to ask, well, what is this new function A? How are we defining A? Right? We are taking, let's see, we are integrating over S. I believe this is still momentum, right? I'm curious why it's over P space and not Q space. PQ. Anyway, so let's take this at face value, what we're looking at. So again, we are taking an integral. So we're looking, and we're a normalized integral over a 3n number of dimensions, right? So we're adding them up over all these dimensions. But now we have this other variable s, and s is kind of a dummy variable, right? Because we're adding up all s's, there's not going to be any s in the outcome. It's just a stand-in variable that we're integrating over. All right. And then we're taking our operator and we are putting it in. So we have this, this complex exponential, which is, if you squint at it, looks kind of like a Fourier transform. Hint, hint. And then we are taking the inner product over p plus s over 2 and p minus s over 2. So for some position p, right, I'm looking at minus s over 2 plus s over 2 as I vary s, right? So I end up covering all of s space in this integral, which is why there's no s in the output function. But so yeah, so I'm doing this integration over this, and that gives me the my Weyl symbol operator version of A, right? You can kind of think of this as similar to a Fourier transform of A, but in this case, it's a different transform. It's a transform into Weyl space. Okay. Weyl symbols for common operators like P, Q, P squared, Q squared, H, H squared, etc. Can easily be calculated directly from 2, right? From this. The Wigner function of the many particle system in canonical ensemble is defined as a Fourier transform of the off-diagonal matrix elements of density matrix in the coordinate representation. Well, let's just finish this sentence and then we'll look at what that is. Okay, so WPQ, beta V, right, is Z again is our partition function, so that's kind of telling you the set of possible states, and then we're integrating over, looks like dummy variable. Let's see. Eta is clearly a dummy variable. Yeah. Oh, I'm sorry. For some reason I thought it was also integrating over rho. Okay. So we're integrating over this dummy variable eta, which, of course, this part looks a whole lot like what we were talking about up here, right? Where we're taking the distance minus and plus some central point, and we're just taking all the possible distances minus and plus at central point. Exactly the same format. This is the Weyl space, Weyl function, Weyl distribution, whatever format that you'll see all the time. And of course, we're just integrating because it's a transformation. We're integrating over this dummy variable eta. Okay, and Z is the... What is rho then? Is rho just density? Yeah. So this is a density matrix. So what this... Let's see. Boy. Is density matrix in terms of change in density? That's actually a good question. Hold on. I need to look this one up because this is a little outside my standard area of research. So let me see. Density matrix. Let's see how this is defined. Okay, called the density operator. Density matrix representation of a linear operator called density operator. Density matrix is obtained from the density operator by choice of orthonormal basis. Fine. Practice terms density matrix are often interchangeable. Okay, because space, one or two-dimensional Hilbert space. Density operator is that where the diagonal elements are real numbers that sum to 1. The off-diagonal are complex conjugates of each other. They're restricted magnitude to the requirement to be semi-definite operator. Okay, I didn't say positive semi-definite. Sorry, one second. I'm just reading this through real fast here. Okay. Yeah. All right. So if we have a single state, all right. Right. So okay. Oh, right. The sigma x, sigma y, sigma z's. I forgot about these block sphere stuff. Okay. This is 1-0. Okay. So rho ij is what's p uses? This is a different p variable. This is a different p variable. What are you using as a variable for p here? Okay. Right. It's just a two-dimensional matrix. I know what I want. Why are you not helping me? Okay. Let's find a better definition. Sorry for the, It's been a while since I've touched this stuff. Anyway. Consider observable A in a pure state psi with the expectation given by that. The density matrix for a pure state is given by T is psi. Okay. Okay. Expectation value of observable A in a state is represented by the density matrix rho given by that. Okay. This is a little more annoying than I really wanted to get into. Yeah, this is way more annoying than I really want to get into. Your matrix satisfies the Neumann equation. Wait for all right. This commutator and H and Pro. All right. All we really need, I think, for this is typically would be something like P1, P10, P01, P1, right? So this is that complex conjugate of this. And the trace is typically the actual observable that you get from a measurement. All right. I think this is a side quest that we don't need to go too deep into. We'll see if that's true. As of right now, I'm going to put a pin in this and say, this is a side quest. We don't really need to hit this too hard. Let's move on to other things. Because that's a whole other can of worms, which with a little bit of going through and remembering what's going on, I could explain, but that would take a while. That's a longer project than I want to do here, where I'm trying to understand the path integral portion of this. So again, I think right now this is a side quest. We'll see if it comes back again. Okay. So where were we? All right. So Z is the partition function of an ensemble of n particles. Beta is 1 over kT, so that's your representation for temperature. V is volume. We mentioned that before. Okay. P is P1, P2, Pn. So the momenta, that's the set of the momenta of all your n particles, right? So there are n different particles, are all moving in different directions, so each one has their own momentum as a vector. That's why that's bold. Q is the position of our n particles, again as a vector. And PQ is the sum of PAQA, right? So PQ equals P1 Q1 plus P2 Q2 plus ... right? For all of your n particles. Hamiltonian of the system consists of the kinetic and potential parts. Again, a Hamiltonian is kinetic energy plus potential energy, where kinetic energy is the sum over all particles of p squared over 2m. This is just the kinetic energy to momentum relationship. The potential energy is the potential energy of each of the individual particles interacting with each other and or external fields, right? So we don't really have enough information to talk about what that potential energy is. For simplicity, we'll consider a system consisting of identical particles of mass m. Generalization on a system with several kinds of particles is direct. The Wigner function, W of PQT, being the analog to the classical distribution function in the phase space, has a wide range of applications in quantum mechanics and statistics, right? So again, W is not just about this, it's about a bunch of different things. For spinless bosons or fermions, the density matrix in the canonical ensemble looks like this. Where the symbol P denotes particle permutations, +1 corresponds to the Bose statistics, -1 to Fermi statistics. Okay, so P, this P here is the permutations. Why is it only on that side? That's interesting. Right, so rho is a function of Q 8 over 2 and Q plus 8 over 2, right? Because this is our, essentially our W. Oh, okay, that's the plus or minus 1, right? So we're summing, so it depends if we have bosons or fermions, right? Different types of particles act differently. Some of them can overlap, some of them can't. So we're summing over P particles, and this looks very, very similar to our transformation into the Wigner space, but we have this permutation piece here, which is interesting. So our Hamiltonian is in the exponent there. That's fairly typical. So I'm curious why, right? We have this particle permutations only on one side of this. That's the thing that gets me. That's what I'm not sure about. Okay, since kinetic and potential energy in Hamiltonians do not commute, an exact, explicit analytical expression for the Wigner function does not exist. To overcome this difficulty, let us represent the Wigner function similarly to path integral representation of the partition functions. So we will represent our statistical operator, e to the negative beta h hat, as the product of a large number m of operators, e to the minus epsilon h hat, formally related to high temperature, epsilon equals beta over m, and write down the Wigner function in this form of multiple integral products of the high temperature and density matrices. So again, beta is a function of temperature, right? It's 1 over kT. So we are dividing our beta by m particles, large number of particles. Okay, so we're saying that W then is our partition function, which kind of lists out all of our available states. And then we're integrating over eta. So we're integrating over this dummy variable for this piece. So this is kind of ends up being a constant here. And then we are integrating over (3n) and then m minus 1. Oh, hold on. Q. Oh, okay. I see. Okay. Equal 0, m minus 1. So we're doing the multiply, okay, of q m plus 1 for q naught equals oh mama man. Okay. So we're sort of see what's going on. So these are our limits of our integration. So that's where our q plus 8 over 2 and q minus 8 over 2 are coming in, right? P is the possible permutations of it. We've got we have our product of a large number, so it represents this statistical operator as a product, right? So we're saying because beta is a function of temperature and that's a statistical property, we're going to talk about the quote-unquote temperature of each individual particle, and then we're going to integrate over all those particles, right? That's what gives us our quote temperature unquote, right? So that's what's going on with this integral is we're adding up over all the particles, there's portion of the temperature, if you will, and then we have to, let's see, this is a so this is the product of our operators here, right? This is our there's our Hamiltonian up there, negative epsilon h, right? And that's operating on qm plus 1. So it would be like psi 0 star e to the negative epsilon h psi 1, right? Is kind of what you're doing. Sorry, iterating that, right? And so that's what this inner product is. And then the limits of our integration are between these two spots, between Q naught and QM. In a limit where epsilon approaches 0, the high temperature density matrices can be easily calculated with an accuracy up to order of epsilon squared, where okay, the inner product between QM and this operator and m plus 1 is equal to lambda epsilon to negative 1, where there's your, it's just a constant, right? It's the thermal wavelength at temperature m times t, times the exponential of negative pi. There's our lambda again, right? So again, lambda is just this constant. Q is the momentum of particle. Oh, I'm sorry. Yeah. Of particle m plus 1 minus the momentum of particle m squared, right? Minus epsilon. So again, epsilon is approaching 0. Interesting. So does that mean this part is approaching 0? Let's see. U of qm So here's my question. If epsilon is approaching 0, can we drop this? I don't know what that U function is. I'm not sure what the U function is over here. But I suspect what this allows you to do, since epsilon is approaching 0, you can probably just drop that, right? And so this is the sum from a equals 1 to n of the momentum of particle A in state m plus 1 minus particle A in state m. Okay. Okay, thus the expression for the Wigner function takes the form. All right, we just plugged that into here. Okay. No, it still has that U. I'm curious how that U is going to come up. Again, where lambda is the thermal wavelength of at temperature T. The continuous limit m approaches infinity. This expression turns into the path integration over trajectories q of tau, starting at point q minus some constant and ending at q plus at p of q plus constant, where tau is a dimensionless parameter, which may be interpreted as, quote, imaginary time. Okay. So that's the since things are operating as complex values here, it's just the complex portion of the time. I'm sorry, it's the imaginary portion of the complex time variable, which drops out when you multiply by the complex conjugate, right? So that imaginary time piece is going to drop out when you do the any actual operation that yields a measurement, but you still have to take into account when you're doing the math. Okay. So let's see, W of PQ beta V now is we have our what's it called? Our not distribution function. Yeah, distribution function. No. Yes? What? Why am I forgetting the name of that? Not distribution function. Partition function. There we go. There. So we have our partition function again, which is telling you the set of states that are available for specific temperature and volume. We are integrating over all of our particles, right? This ends up being a constant here, right? Because we're integrating. No, it's not a constant because that's still a function of p, but we're integrating over eta. This whole thing over eta. My bad. We're integrating over our dummy variable eta that is in this exponential piece, and it also is in the limits of our integration. So we're integrating our set of integrals. Okay. So times, okay, and this is our exponential. So q, this is velocity, right? Because it's the derivative of position over tau, which is our, quote, imaginary time tau. All right. And d is the other operation that we're going to talk about later, right? But this is a derivative over all 3n all 3n dimensions that exist in this space. Okay. Measure of the path integral depends on Fourier variables eta and position q. To get rid of this dependence, we change the variable from trajectories q of tau to closed dimensionless trajectories z of tau, where q of tau is lambda z of tau. Okay. Z. Taking into account new boundary conditions, z of 0 equals 0, 1 equals 0. So all we've done is parameterized q into this dimensionless thing z, such that instead of going over all this tau, it's just going over between 0 and 1, right? We obtain a desired path integral representation of the Wigner function. This is what we kind of wanted. All right. Regularization of identical particles, and D is integration over trajectories. Okay. So we are integrating over all trajectories, right? Here's our 0 to 1, right? This is why we changed variable types from 0 to 1, so we can integrate Z that way. Still doesn't explain what U is as a function. Anyway, so this is over all of our paths, right? And we're integrating as Z goes as 0 of 0 equals Z of 1 equals 0, okay? And we're integrating everything over all particles. This is wacky. I'm going to see if we have a better... okay. So this is going a little bit over my head in terms of explanation. Like, I'm getting bits and pieces of it. I don't think I'm getting it well enough to be able to explain what's going on. Let's see. But I did download other versions of this. There might be better papers for this. Beginner function as a phase-space target. Okay, so we might look at that, and then what's this? Oh, that's the model performance one. Okay, let me think. There's too much background stuff here that's clogging up the math, and that's causing issues. Right? Because we really just want the math piece of it. But there's a lot of quantum mechanical background that's causing us problems. So what's the best way out of this? Let me think. Apparently the best way out of this is to splash juice all over myself. Whoopsies. All right. I think we need to rethink the approach, right? This approach isn't producing the positive effects I was hoping, and so we have to take a step back and rethink our approach. What are the core things we're looking for? We're looking for the Wigner distribution and the path integral process over it, right? This is assuming a lot of other quantum effects that are going on, and a lot of other descriptions, particle descriptions are going on that I think we could eventually get if we were to go and dig deep enough. But I don't think this is providing us what we need, right? Because we have to ask, what are we actually doing this for, right? We're doing this for the other math. We're not doing it for this. So that's on me. I think I picked a bad paper. I'm going to have to find another paper that is appropriate for this. That may take a little bit, given all the work I have to get done in the meantime. So I think what I'm going to do is I'm going to stop this here. Maybe after we've gone through more of the path integral stuff, we could come back to this and reapproach it in a way that's more intelligible. But if I'm being overcrowded by too much other stuff, then I can't explain it to you guys, which means I don't learn it in my explanation to you guys, and you guys can't learn it and help me with it. So, I think what we're going to do, we gave this an honest shot, but I think this is the wrong approach. So, I'm going to find another paper covering this subject that's a little bit more tuned to what we're looking at. And for next week, I think what we'll do is we'll move back to a philosophy paper or something, right? Something a little different. We'll cool our jets a little bit on this. And then we'll come back for more of this at a later point. I think that's the appropriate way to go. So I'm sorry for those of you who showed up and were hoping we would really crank through this and get something useful on the way out on the other side of it. That's my bad. I picked an improper paper for this, so we will reattack this at a later date. In the meantime, our next stream will be what I have it as. I think it is Monday. Did I have it as Monday? What did I have it as? Hello. Where is my schedule? Let's see. I'm sorry. Wednesday would be the next planned stream. As a reading thing. Yeah, we'll do a reading, because our gaming streams we just sort of randomly shove in there whatever we want. So we'll do another reading stream. We'll do another chapter of The Hobbit and maybe some short stories on Wednesday. Friday we'll go back to our analysis of the other paper that was actually being very fruitful and very useful. I do want to figure out times. I do have to figure out better times. Yeah, so 5:15 Eastern Standard Time for Wednesday. I have to go back to the state where I had one of my streams earlier in the day. But I don't know what stream that will be. Maybe I'll change the reading stream to earlier. Hey, that's the right move. Maybe the Wednesday stream gets moved earlier. I have to figure it out. I just don't want to leave people who are in different places behind and not able to join in with any of the streams. Just afternoon if possible. Yeah, we could try doing a noon o'clock stream at some point. We have to see. We're still experimenting. This is still a young channel. We're still figuring out how to do things. It's going to evolve over time, and that's fine. That's just how this works. So, or 1 o'clock better. Okay. Yeah, we'll figure something out. You mean on Wednesdays or just in general? On Wednesdays specifically. Okay. Okay. Yeah, maybe we could do Wednesday at 1. That might be a way to go. Might be a good plan. Okay, anyway. This is neither here nor there. This is not something that needs to be fully figured out today. But I will send out messages and notifications on when we're going to be streaming next. As of right now, we'll plan for Wednesday at 5:15 p.m. Eastern Standard Time. That is what's on the schedule. That is what we will plan for as of right now. If that is going to change, I will notify people. Yes. So anyway, I hope you guys have a good rest of your Sunday and weekend. I have to go back to doing work. So you guys have a wonderful one. Again, I'm sorry for this Sunday morning paper crashing and burning. That was on me. I picked the wrong paper. It happens. So we'll figure out a better one for our next go round. Okie dokie. Well, you guys have a wonderful one, and I will see you next stream, which is either going to be Wednesday or I'll stream earlier because I randomly hop on stream to play a game. Who knows? But the latest will be Wednesday. So I'll see you later. Goodbye.